These are the notes from Chapter 12, the back half of Chapter 12, talking about torque and rotational dynamics and equilibrium. These set of notes are going to go through just the first about half of the slides and mostly talking about torque. So torque, if you think about opening a door and you've got a hinge on the left, so you're looking at a top view of a door. Four pushing forces are shown, all of equal strength. Which of the forces is most effective at opening the door? And you would clearly state that when you open a door, you want to push at a 90-degree angle, and you want to push as far away from the hinge as possible. If you've tried to push close, that's difficult. This isn't going to turn the door in any way, shape, or form. And so the ability of a force to cause a rotation depends on three factors. It depends on the magnitude of the force, so how big it is, and these are all the same. The distance r from the point of application to the pivot, so however you are from this point. So if you're close, that's not going to give you a big ability to rotate the door. These two would be the same, but then they have a different angle. And you can think about this as components. Here you want the force to be perpendicular if possible, so there is a piece of this force that is perpendicular, but it's only a tiny piece. It would be like right in here. So torque is defined, the symbol for torque is the Greek letter tau, right here. Looks like a fun CT. And they've got here the kind of a mathematical symbol. The r is the distance, the f is the force, and then the sign of the angle between them. So here we want to rank in order from largest to smallest the 5 torques. The rods all have the same length and are pivoted at the dot. So here you've got one at the middle, you've got a smaller one at the middle, you've got a smaller one here at the end. The C is not going to do anything at all because that's not going to pull. And then I've got 4 at the end, and it's pulling at an angle of 45 degrees. So I'd have sine of 45 is about 0.7 of 4, which is going to be probably bigger. So and this would be the same as a 2 at the end. So E is going to be the biggest. And then A and D will be equal. And then B is going to be next and C is going to be last. So A here would be the correct answer. Alright, so here is our first question. Louise uses a 20 centimeter long wrench to turn a nut. The handle is tilted 30 degrees above the horizontal, and he pulls straight down in the end with a force of 100 newtons. How much torque does he exert? So I'm going to do a pen here, and torque equals FR sine of the angle. And so my force is 100. My R is 0.2 meters. And then I have the sine of 30, which happens to be a half. So when you run those calculations, you come out to 10. And the units are a force, Newton, and a distance, meters. So it's a Newton meter. If you do a lot of stuff with cars or any kind of mechanical stuff, you might have torque wrenches that are in foot-pounds. Those would be the British units. Alright, so now we need to compare force versus torque. So in linear land, a force will change an object's linear motion, so it will cause it to accelerate, and we get F equals ma. In the rotational world, a torque will change an object's rotational motion, and the force here becomes, and I just want to go back to a pointer, arrow. Okay, so here force becomes torque, and the mass becomes that rotational inertia, or that moment of inertia, and the A in meters per second squared becomes the alpha. And remember that we have this quantity here to change from radians per second squared to meters per second squared. So The other thing is that, we had F equals ma. That's Newton's second law. We had, back in linear land, we talked about if there's no net force, the object will either stay at rest or stay moving at constant velocity. That was Newton's first law. And so the same rule applies here, but now it's if there's no net torque, the object either stays at rest, it does not rotate, or it rotates with constant angular velocity. So here again, a student holds a meter stick straight out with one or more masses dangling from it, rank in order the most difficult to least difficult. So again, here, the 500 grams is out as far as it can be. A and B should be the same because this one's halfway in. C is going to be much larger. And D is going to have a component, the 500 is out at the end, but it also has a 500 in the middle. And so C should be the biggest, followed by D, and then A and B will be equal. So D here should be the correct answer. All right, and so just like we did F equals ma plus kinematic problems, we can do rotational kinematic plus torque problems, where instead of F equals ma, we have torque equals I times alpha. So an engine in a small airplane is specified to have a torque of 60 Newton meters. Oops, I'll back that up. And I want a pen. Let's get that pen in blue. All right, so my torque equals 60. I need to find the I value for this, and a propeller is basically a long stick in the middle, and so that's 1/12 ml squared. So 1/12, the mass is 40, and the length is 2, and we have to square that. And so I get a value here of 13.33. And so very similar to F equals ma, I could find A. Here I can find alpha is the torque divided by this moment of inertia. So I have 60 divided by the 13.33 equals 4.5 radians per second squared. And so now that I know essentially the acceleration, and it starts from rest, so VO equals 0, I've got the final velocity is 200 rev per minute, and I need to convert that to radians per second. So 1 rev is 2 pi radians, and 1 minute equals 60 seconds. And if I calculate that out, it's 21 radians per second. And then I know A, and it's asking me to find the time. So the time is just V minus VO over A. So I have 21 minus 0 over 4.5. And this comes out to be 4.7 seconds. So again, it's a kinematics, but then it's an F equals ma, all in the rotational world. And that is where we will leave off. We will continue with these notes tomorrow.